Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The roar of rocket engines has echoed across launch pads for over 60 years, but until recently, each thunderous ascent represented a spectacular act of destruction. Every Saturn V that carried Apollo astronauts to the moon, every space shuttle that orbited Earth, and countless unmanned missions relied on rockets designed to be used once and discarded forever. This fundamental reality shaped space exploration for decades, making each launch extraordinarily expensive and limiting humanity's reach beyond our home planet. The economics were staggering. A single Falcon 9 launch in the early 2010s cost approximately $62 million, with the first stage booster, representing roughly 70% of the total vehicle cost, plummeting into the ocean after just 8 minutes of flight time. Imagine purchasing a commercial airliner, flying it once from New York to Los Angeles, then abandoning it in the Pacific Ocean. This wasteful approach seemed not just inefficient, but fundamentally unsustainable for any meaningful expansion into the solar system. The concept of rocket reusability wasn't entirely new. NASA's Space Shuttle program, operational from 1981 to 2011, represented the first serious attempt at partial reusability. The orbiter could indeed be refurbished and flown again, completing 135 missions over 3 decades. However, the complex refurbishment process between flights often took months and cost hundreds of millions of dollars per mission, making it arguably more expensive than traditional expendable rockets. Everything changed on December 21, 2015, when SpaceX achieved what many considered impossible. The Falcon 9 first stage booster, after successfully delivering 11 Orbcomm satellites to low Earth orbit, executed a controlled powered descent back through Earth's atmosphere. Instead of crashing into the ocean, it fired its engines one final time and touched down vertically at Landing Zone 1 Cape Canaveral. The precision was breathtaking. A rocket moving at thousands of miles per hour had slowed itself to a gentle touchdown on 4 landing legs. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning. And your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. This moment represented more than just a technological achievement. It fundamentally challenged the accepted physics and economics of spaceflight. Engineers had long understood the theoretical possibility of rocket recovery, but the practical challenges seemed insurmountable. The booster had to survive temperatures exceeding 2,000 degrees Fahrenheit during atmospheric re-entry, execute split-second engine relighting sequences, and land with pinpoint accuracy while carrying minimal fuel reserves. The implications rippled through the aerospace industry immediately. Traditional launch providers, who had dominated the market for decades with expendable rockets, suddenly faced competition from a company offering dramatically reduced costs through reusability. Within months, SpaceX began reflying recovered boosters, proving that rocket reuse wasn't just possible but commercially viable. Blue Origin, founded by Amazon's Jeff Bezos, had actually achieved the first successful rocket landing with their New Shepard vehicle in November 2015, just 1 month before SpaceX's milestone. However, New Shepard was designed for suborbital flights, reaching altitudes of approximately 62 miles before returning to Earth. The technical challenges of orbital-class rocket recovery were exponentially more complex, requiring the booster to reach speeds of nearly 17,500 miles per hour and survive the intense heating and structural stresses of orbital velocity. The success of that December landing validated years of iterative development, countless simulations and bold engineering decisions that many established aerospace companies had dismissed as reckless or impossible. SpaceX had demonstrated that the fundamental economics of space access could be revolutionized through engineering. Innovation rather than simply scaling up existing technologies. Recovering a rocket booster requires solving one of the most complex engineering challenges in aerospace: transforming a vehicle designed to accelerate payload to orbital velocity into a precise landing system capable of touchdown accuracy measured in meters. The physics involved pushed the boundaries of what's possible with current technology, demanding innovations in materials, science, guidance systems, and propulsion control that didn't exist when expendable rockets dominated spaceflight. The first challenge begins during stage separation, approximately 2.5 minutes after liftoff, when the first stage booster separates from the second stage at an altitude of roughly 45 miles. At this moment, the booster is traveling at approximately 3,500 miles per hour and following a ballistic trajectory that would naturally carry it hundreds of miles downrange. To return for landing, the booster must execute a complex series of maneuvers that seem to defy intuition. The booster flip maneuver represents perhaps the most critical moment in the recovery sequence. Using cold gas thrusters and grid fins, titanium control surfaces that extend from the rocket's sides, the booster rotates 180 degrees to point its engines in the direction of travel. This orientation allows the Merlin engines to fire in a boost-back burn, literally pushing against the booster's forward momentum to reverse its trajectory toward the landing site. Grid fins, originally developed for military applications, serve as the primary aerodynamic control system. During atmospheric flight, these lattice-structured surfaces, each weighing approximately 1,000 pounds, can withstand temperatures exceeding 2,000 degrees Fahrenheit while providing precise flight control. The fins adjust continuously throughout descent, responding to guidance computer commands at rates of up to 10 times per second to maintain the optimal flight path. Atmospheric re-entry presents extraordinary thermal and structural challenges. As the booster descends through increasingly dense air layers, friction generates temperatures that would melt most materials. The rocket's aluminum structure experiences thermal expansion and contraction that could compromise structural integrity if not carefully managed. SpaceX engineers developed specialized heat-resistant coatings and thermal protection systems specifically designed for multiple reuse cycles. The entry burn phase occurs at approximately 40 miles altitude when 3 Merlin engines fire for approximately 20 seconds to reduce velocity and heating loads during the most intense portion of atmospheric re-entry. This burn slows the booster from approximately 3,000 miles per hour to roughly 1,000 miles per hour, significantly reducing the thermal stress on the vehicle structure and heat shield systems. Terminal guidance represents the final and most precise phase of the landing sequence. Beginning at approximately 3 miles altitude, sophisticated radar systems and inertial navigation units work together to provide real-time position and velocity data accurate to within centimeters. The guidance computer processes this information at lightning speed, calculating the exact engine throttle commands needed to achieve a soft touchdown. The landing burn itself lasts only 20 to 30 seconds, but requires extraordinary precision. A single Merlin engine throttles down to approximately 40% of maximum thrust, the minimum sustainable throttle setting, while the guidance system makes final trajectory corrections. The engine must reignite reliably after minutes of cold soak in the vacuum of space, provide precise thrust control, and shut down at exactly the right moment to achieve zero velocity at ground contact. Structural loads during landing present. Unique engineering challenges not encountered in traditional rocket design. The landing legs must absorb the impact energy of a 150,000-pound vehicle while maintaining stability on uneven surfaces. Each leg incorporates sophisticated shock absorption systems and can adjust independently to accommodate landing site irregularities. The achievement of successful rocket recovery required fundamental advances in computational guidance algorithms, real-time trajectory optimization, and autonomous flight control systems that have applications far beyond spaceflight, influencing everything from autonomous vehicle development to precision manufacturing systems. The transition from expendable to reusable rockets has triggered the most significant economic disruption in the space industry since the dawn of the space age. Traditional launch costs, which had remained stubbornly high for decades despite technological advances, suddenly became negotiable as reusable systems demonstrated the potential for order-of-magnitude cost reductions that industry experts had long considered theoretical. SpaceX's cost reductions have been nothing short of revolutionary. A Falcon 9 launch using a previously flown booster now costs approximately $50 million compared to the $62 million price for expendable missions. More importantly, SpaceX's internal costs have decreased even more dramatically. Company executives have stated that the marginal cost of a reused Falcon 9 launch, excluding development and infrastructure costs, has dropped below $15 million per mission. These savings compound rapidly across multiple flights. A single Falcon 9 booster designated B1051 has completed 19 successful missions as of 2024, representing a cost savings of over $400 million compared to using expendable rockets for the same payload delivery capacity. The booster has delivered everything from Starlink satellites to crew missions to the ISS, demonstrating the versatility and reliability of reused hardware. The ripple effects have transformed entire market sectors. Satellite deployment costs have plummeted from approximately $20,000 per kilogram to orbit down to approximately $3,000 per kilogram for dedicated launches, with rideshare missions offering even lower costs. This dramatic reduction has enabled new categories of space-based businesses that were previously economically unfeasible. The small satellite revolution exemplifies this transformation. Companies like Planet Labs can now deploy fleets of hundreds of small Earth observation satellites, providing daily global imagery at costs that would have been prohibitive under the old expendable rocket paradigm. The entire CubeSat industry, built around standardized 10-centimeter cube satellites, has exploded from a few dozen launches per year to thousands, enabled primarily by reduced launch costs. Commercial space stations represent another emerging market enabled by reusable rockets. Companies like Axiom Space are developing private orbital facilities that depend entirely on affordable, frequent transportation to low Earth orbit. Without reusable rockets, the economics of commercial space stations would remain untenable, requiring government subsidies or pricing that would limit access to only the wealthiest organizations. Space manufacturing has emerged as a legitimate commercial prospect for the first time in history. Companies are now seriously investigating orbital factories for producing fiber optic cables, pharmaceutical products, and advanced materials that benefit from the microgravity environment. The key enabling factor is not just reduced launch costs, but the reliability and frequency of reusable rocket systems that make regular cargo transport economically viable. The traditional space industry has been forced to respond dramatically. United Launch Alliance, the joint venture between Boeing and Lockheed Martin that dominated U.S. government launches for decades, has developed the Vulcan rocket with partial reusability features. European Space Agency member nations have accelerated development of the Ariane 6 rocket and are investigating reusable technologies for future vehicles. Launch frequency has increased exponentially. SpaceX conducted 31 launches in 2020, 61 launches in 2022, and is targeting over 100 launches annually by 2025. This dramatic increase in launch cadence was only possible through reusability, as manufacturing enough expendable rockets for such flight rates would require massive industrial capacity expansion. The economic model extends beyond simple cost-per-launch calculations. Reusable rockets enable new mission architectures that were previously impossible. Satellite servicing missions, space debris removal operations, and orbital assembly projects all become economically feasible when transportation costs drop by an order of magnitude and flight opportunities increase proportionally. International competitiveness has shifted dramatically. Countries and companies that fail to develop reusable rocket capabilities find themselves at severe economic disadvantages in the global launch market. China has accelerated development of reusable Long March variants, while private companies worldwide are pursuing similar technologies to remain competitive in the transformed marketplace. The evolution of reusable rocket technology has progressed far beyond simple booster recovery, developing into sophisticated systems capable of handling increasingly complex mission profiles while maintaining economic efficiency across diverse payload requirements. This technical maturation has required fundamental advances in engine design, structural engineering, and mission planning that push the boundaries of aerospace engineering. Engine reusability presents unique technical challenges not encountered in expendable rocket design. The Merlin engines powering Falcon 9 boosters must withstand multiple exposure cycles to the extreme temperatures, pressures, and vibrations of rocket flight while maintaining precise performance characteristics. SpaceX has iteratively improved engine design through multiple generations, with current Block 5 boosters featuring engines certified for 10 flights without major refurbishment. The Raptor engine, designed for SpaceX's Starship vehicle, represents the next generation of reusable rocket propulsion. Unlike the kerosene-burning Merlin engines, Raptor burns methane and liquid oxygen in a full-flow staged combustion cycle, the most efficient rocket engine cycle ever successfully implemented. This design choice enables deeper throttling capability, essential for precision landing, while methane's combustion characteristics reduce coking and engine degradation between flights. Structural adaptation for reusability has required innovative engineering solutions. Falcon 9 boosters experience thermal cycling from -200 degrees Fahrenheit in space to over 1,000 degrees Fahrenheit during atmospheric re-entry, then back to ambient temperatures at landing. The aluminum-lithium structure must accommodate these temperature swings across dozens of flight cycles without developing fatigue cracks or losing structural integrity. Grid fin technology has evolved significantly since early Falcon 9 flights. Initial aluminum grid fins frequently burn through during high-energy re-entries, leading to the development of titanium grid fins manufactured using advanced machining techniques. These fins can withstand temperatures exceeding 2,500 degrees Fahrenheit while providing precise aerodynamic control throughout the entire descent profile. Mission flexibility has become a defining characteristic of modern, reusable rockets. A single Falcon 9 booster might launch a heavy geostationary satellite on one mission, then carry 60 Starlink satellites to low Earth orbit on its next flight, followed by a crew mission to the ISS. Each mission profile requires different flight trajectories, payload configurations, and recovery parameters, yet the same booster handles all variants successfully. Starship represents the ultimate expression of reusable rocket technology, featuring full reusability of both first and second stages. The Super Heavy booster, standing 230 feet tall, will return to the launch site for capture by mechanical arms, eliminating the need for landing legs and enabling rapid refurbishment. The Starship upper stage, capable of orbital, flight and precision landing, can deliver over 100 tons to low Earth orbit, while returning intact for reuse. The technical challenges of full reusability exceed those of booster recovery by orders of magnitude. The Starship upper stage must survive orbital re-entry at speeds approaching 17,500 miles per hour, execute a complex atmospheric flight profile using aerodynamic control surfaces, and perform a precision landing burn, using the same engines that powered its ascent to orbit. Heat shield technology for full reusability has required breakthrough innovations. Starship employs thousands of hexagonal steel tiles designed to protect the vehicle during atmospheric re-entry while remaining lightweight and easily replaceable between flights. Unlike space shuttle thermal protection systems that required extensive inspection and refurbishment, Starship tiles are designed for minimal maintenance across hundreds of flight cycles. Propellant loading and handling systems have evolved to support rapid reusability. Traditional rockets require days or weeks of preparation between flights, but reusable systems target turnaround times measured in hours. This requires automated propellant loading systems, advanced health monitoring sensors, and streamlined inspection procedures that can verify vehicle readiness without extensive manual intervention. Quality assurance for reusable vehicles presents unprecedented challenges. Each component must be certified for multiple flight cycles while maintaining the same reliability standards as expendable rockets. This has led to development of advanced non-destructive testing techniques, real-time structural health monitoring systems, and predictive maintenance algorithms that can identify potential failures before they occur. The integration of artificial intelligence and machine learning into reusable rocket operations has become essential for managing the complexity of multi-flight vehicle management, optimizing landing trajectories in real time, and predicting maintenance requirements based on flight history and sensor data analysis. The maturation of reusable rocket technology represents far more than an incremental improvement in space transportation. It fundamentally enables humanity's expansion throughout the solar system by making interplanetary travel economically sustainable for the first time in history. The same engineering principles that allow rockets to land back on Earth are now being adapted for operations on Mars, the Moon, and beyond. Mars colonization, long relegated to science fiction, has become a serious engineering challenge primarily because reusable rockets can deliver the massive cargo volumes required to establish sustainable human settlements. Traditional expendable rockets could never provide the economic foundation for Mars development, but reusable systems capable of delivering 100 tons or more per flight make large-scale Mars operations feasible. Starship's design specifically targets Mars mission requirements. The vehicle's methane-burning Raptor engines can be refueled using resources available on Mars, where carbon dioxide from the atmosphere and water ice from the soil can be processed into methane and oxygen propellants through the Sabatier reaction. This in-situ resource utilization capability transforms Mars from a one-way destination into a refueling station for deeper solar system exploration. The economics of Mars settlement depend entirely on reusability. Establishing a self-sustaining Mars colony requires transporting millions of tons of equipment, supplies, and eventually people across the 200 million-mile gap between Earth and Mars. Even with reusable rockets, this represents a multi-trillion-dollar undertaking, but expendable systems would make the project economically impossible regardless of available funding. Asteroid mining has emerged as a legitimate commercial prospect enabled by reusable transportation systems. Near-Earth asteroids contain vast quantities of platinum, rare earth metals, and water that could support both Earth-based industries and space-based operations. The key breakthrough is not just reaching asteroids, but returning valuable materials to Earth or processing them in space for local use. A single metallic asteroid like 16 Psyche contains an estimated $10,000 quadrillion worth of metals, more than the entire global economy. While extraction and processing technologies remain under development, reusable rockets provide the transportation foundation that makes asteroid resource utilization economically viable. Regular cargo flights between Earth and asteroid mining operations become feasible when rockets can be reused dozens or hundreds of times. Space-based solar power represents perhaps the most transformative application of large-scale reusable rocket capabilities. Orbital solar power stations could generate continuous electricity without weather interference or day-night cycles, potentially providing clean energy to Earth while supporting space-based operations. However, constructing gigawatt-scale orbital power stations requires transporting millions of tons of materials to orbit, only possible with highly reusable, high-capacity transportation systems. The Moon has re-emerged as a crucial stepping stone for deep space exploration, enabled by reusable lunar transportation systems. NASA's Artemis program plans to establish a permanent lunar base that could serve as a refueling depot, manufacturing center, and staging area for Mars missions. Lunar water ice can be processed into rocket propellants, while the Moon's low gravity makes it an ideal location for assembling large interplanetary vehicles. Interplanetary transportation networks enabled by reusable rockets could transform the solar system into an interconnected system of worlds and stations. Regular cargo runs between Earth, Mars, and the asteroid belt become routine when vehicles can be refueled and reused at each destination. This creates the foundation for a true space-based civilization that extends human presence throughout the solar system. Space manufacturing scales dramatically when transportation costs drop by orders of magnitude. Products that benefit from microgravity, vacuum, or extreme temperatures can be manufactured in space and delivered to Earth markets economically. Everything from advanced semiconductors to pharmaceutical products to ultra-pure crystals, could be produced more efficiently in space than on Earth's surface. The timeline for these developments has compressed dramatically due to reusable rocket capabilities. Mars missions previously planned for the 2060s are now targeted for the 2030s. Asteroid mining demonstrations could occur within the next decade rather than the next century. The transformation from a single-planet species to a multiplanetary civilization may unfold over decades rather than centuries, fundamentally altering humanity's long-term survival prospects and opening unlimited resources for continued development and exploration.